let's just talk about linear combinations, spans, and basis vectors in today's video. So let's start with linear combinations. So essentially if I have vector A and vector B, the linear combination of these two vectors will just be S1 times A plus S2 times B. So this is the linear combination of vector A and B. So how does this work? So what are S1 and S2 in the first place? So S1 and S2 are real numbers, so any real numbers. So you can just choose any real value for S1 and S2 on your choice. So they're real numbers. And basically, what does this mean? So firstly, what does the linear combination of vectors A and B result in? This is another vector. So if we have values S1 and S2 already set, then this is just going to be another vector. So essentially we're using A and B to vectors A and B to create a new vector. So let me just draw this. So this is Y and this is X, the XY plane. Vector A is here, vector B is here. Let's just draw this differently. Okay, vector B is here. Assume they start at the origin, and now we're just using vector A and vector B to the sum of them and also scaling up and down to create new vectors. So essentially, if S1 and S2 are both 1, then the resulting vector would be, so we just sum these two up and we did this. We have a resulting vector like this, right? That's our first linear combination. We also have like other vectors. Say we scale this up by 2 times, or let's scale this up by 1.5 times. If we scale this up 1.5 times, our resulting vector will be something like that. And then we have red. So if we scale the red one up, or let's say we scale it down, we scale it 0.5 times like this, or maybe that's not 0.5, something like that, then the result will be this vector. So as you can see, there's no straightforward relationship. So let's try and sketch another few vectors. Let's say we scale this up, right? And we have our red vector, which let's say we flip it. So we multiply it by -1. The resulting vector will be like this. We can also have another vector, and we scale the vector up like that. Like that. And then we can scale this up. So this is so we have the resulting vector of that. Essentially, if you just draw every single possible linear combination vector, so if you take any vector like this, then you take any vector like this and you add it to another vector. You take any scaling up of A and B and you add the resulting vectors together. Then you'll get all the vectors you can imagine on the 2D coordinate plane. So this is going to be the span. The span of vector A and vector B will be equal to the XY plane. Because essentially, so the span is like the range of this thing. So if this was a function where you inputted S1 and S2, then the span would be like the range. It's like all the possible outputs. In this case, every single possible output vector is in the XY plane. And every single vector in the XY plane is a possible output of every single possible vector in the xy plane is an output of the linear combination of vector A and vector B. Now here by every single vector, I mean vectors that start from the origin. Or actually, yeah, vectors that start from the origin. Okay, so basically now, the span is like the range. So the span is like the range. We also know the linear combination of two vectors is going to be S1 times vector A plus S2 times vector B, where S1 and S2 are scalar real numbers. So, what about some special circumstances? So above, let me just first talk about this. Above, in the above example, vector A and vector B, they were linear independent. So what does this mean? So let me just first tell you what linear dependent means, because these two concepts are the opposite of each other. So let's just talk about where two vectors are going to be linear dependent. So let's say vector C and vector D are linear dependent. So let's just draw the two vectors. Being linear dependent means that the two vectors are parallel to each other. So essentially, if you start from the origin, they'll be on the same line. They'll be collinear, so they'll be on the same line. Maybe their direction is opposite from one another, but they're on the same line. They're all on this blue line here. And this means that they're linear dependent. Essentially, the more formal definition is that you can represent vector C as as S1 times vector D. You can represent vector D as S1 times vector C. Actually, you don't need the 1. Okay, just S times vector D and S times vector C. You can represent the vectors with one another by scaling up another vector. Now, you can't do this for vector A and B because, well, they're just not, you just can't do it. They're not collinear, they're not parallel. So if I try to, so let me just draw this again on this plane. So vector A is probably something like this, right? Vector B is like that. You just can't represent vector A using a scale up or down with vector B, because if you scale vector B up or down, any vector that you get will be on this line. So any vector that you get will be on this line. And vector A is not on this line. And any scale up or down of vector A is also not on this line. So there's no way you can find vector A on this line. It's just not there. And also, if you scale vector A up and down, you get something on this line. However, vector B is just not on this line, so you just can't do that either. So vector A and B are linear independent. So let's talk about, let's see, our basis vectors. Okay. Basis vectors. So the formal definition for basis vectors are basically any vectors that are linear independent and basically they have a span and they have any vectors that have a span of the whole system, of the coordinate system. So this is the formal definition for basis vectors. And what you want here is that, So any vectors that are linear independent and have a span of the coordinate system are, okay, so they're basis vectors. So let me just give you an example. The most common type of basis vectors that we should be familiar with are unit vectors. This one and this one, the two specific unit vectors, vector I and vector j. Vector I is the vector that goes 1 unit in the horizontal direction. Vector j is the unit vector that goes 1 unit in the vertical direction. And the linear combination of these two vectors can form any vector in the 2D coordinate plane. Because as you can see, we can represent any vector using these two vectors. So this is going to be any vector, vector A. Right? So that's how we usually do things. However, there are a lot more basis vectors. There are actually infinite many. Because as long as the two vectors are linear independent, then they can be basis vectors. And they have a span of the whole coordinate system, they can be basis vectors. So these two vectors are also basis vectors because you can create any vector within the 2D coordinate system using the two vectors. So essentially, why do they have to be linear independent? Because if they're linear dependent, like these two vectors here, the green and the black one, then the span of this is not going to be the coordinate system. The span is just going to be the straight line. So this is why they have to be linear independent. So let's also talk about 3D. So for 3D, if you have two linear independent vectors, then their span is going to be a 2D plane that cuts across this 3D system. So if you have any two vectors that are not linear independent, so these two vectors A and B are linear independent, meaning they are not parallel, then the span of these two vectors are going to be let's see, so probably something like this, like a 2D plane. Like this, this 2D plane over here, which cuts through the origin, and it contains the combination of vectors that these two vectors can provide. So this is like the span of the two vectors. It's the result of the linear combination of the two vectors. So this plane here that extends infinitely towards all four directions, like this, and like this. This is like the span of the two vectors A and B. So essentially, if we have three vectors which are all linear if we have three vectors which are all linear independent, so if we want the third vector to be linear independent to the first two, essentially what this means is that the third vector is not on this plane, is not on the span of the two vectors. So as long as this third vector, vector C, is not on the span of vector A and vector B, then we're fine, because vector A and B are already linear independent to produce this 2D plane as a span. And if vector C is not on the span, the 2D plane, then the three vectors are linear independent. This means that the resulting span will be the whole 3D coordinate system. So the three vectors can be the basis vectors. So essentially, if we had vector C, if vector C is on the span of vector A and B, then the resultant span will still be the same plane. if the three vectors are like parallel to each other, the resulting span will be a line. So, and if the three vectors are 0, 0, 0, then the span will be on the origin. So, thanks for